All right, so now let's talk about how to actually compute the exponential of a matrix. And the way we're going to approach this is by computing a few specific but important limiting cases using the series definition of the matrix exponential, which obviously is the only thing you have which defines the matrix exponential formally. And then what we will see later is that once we know these special cases, we can then combine these together to then compute the exponential of a general matrix, or a general square matrix. So the question then is how to compute the matrix exponential. Okay, and we're going to look at some special cases. Okay. All right, so let's start with the easiest possible case one might imagine, which is that you have a matrix which is just diagonal. Okay, so let's say that lambda is a diagonal matrix consisting of, say, lambda 1 to lambda n. All right, then it's easy to check that when you take the powers of lambda, right, you just get the component-wise sort of powers, so lambda 1 to the k all the way up to lambda n to the k. And then you have this. So e to the lambda, right, which is just defined as the sum from k equals to 0 to infinity of 1 over k factorial lambda to the k, right, it's going to be the sum from k equals to 0 to infinity of 1 over k factorial, right, lambda 1 to the k to lambda n to the k. Okay, this is nothing more than this matrix, right, where I'm going to put the sum inside, right, k equals 0 to infinity, 1 over k factorial, lambda 1 to the k, all the way down to k equals to 0 to infinity, 1 over k factorial, lambda n to the k, right? And of course, that's nothing more than the series expansion for the exponential lambda 1 all the way up to lambda n. So this is then e to the lambda 1, e to the lambda n, right? So that's relatively straightforward. So that's one case. Okay, and another case to look at is if A has a full set of eigenvectors, and so you probably know that if A has a full set of eigenvectors, then you can diagonalize the matrix in the following way. So if A has a full set of eigenvectors, right, then you can write A as P lambda P inverse, where lambda is the diagonal matrix consisting of the eigenvalues, right, and then P is the matrix you get. It's like by sort of concatenating, it's like the eigenvectors, the corresponding eigenvectors. Okay, so you have P lambda P inverse. So as before, it's like what I'm going to do is I'm going to try to look at the a to the k power. It's like right. So a to the k power is just P lambda P inverse to the k power, right? But then essentially what happens is that it's like you have the P inverse multiplied by P, those all vanish, so that just ends up being P lambda to the k power P inverse. Okay, so with that in mind, then e to the a, which is again the sum from k equals to 0 to infinity of 1 over k factorial a to the k power, right, by this calculation is just the sum from k equals to 0 to infinity of, I'm going to write this as p, right, 1 over k factorial lambda to the k power P inverse, and I'm actually going to take the P and P inverse outside of the sum, so this is just going to be P sum from k equals to 0 to infinity of 1 over k factorial lambda to the k P inverse, and this is of course just P e to lambda P inverse. Okay, All right, so those are sort of two important cases. And then, of course, the problem is that, of course, in general, A doesn't have a full set of eigenvectors, so you have to introduce this idea of generalized eigenvectors. And when you have generalized eigenvectors, you don't have this kind of nice decomposition. It's like where the lambda inside is diagonal, right? But you can have, it's like you have something which is block diagonal, where the blocks themselves are what are called Jordan blocks. Okay, so that's the third case we're going to look at. What happens if you have a Jordan block? Okay, so we're just going to look at one of those blocks, and then the idea is that because if the matrix A is block diagonal, you can compute the exponentials of the individual blocks. Okay, all right. So the third case is A is a Jordan block. So again, hopefully you remember it's like this from linear algebra, that a Jordan block looks like the following, right? It has a diagonal, right, involving which in this case would be the eigenvalue associated with that subspace, all right, and then you have a sort of something just above the diagonal, which consists of ones along that, okay? Then it's 0, 0, okay? So this looks like lambda I plus this thing, which is 0, 0, 0, 1, 1, 0. Okay, well, let me just sort of make it more general. Okay, and then this is what I call H. Okay, so this is going to be lambda I plus H. Okay, so let me just look at a special case where H is a 3 by 3 matrix, but the conclusion sort of extends more generally. So let's say H is just this 3 by 3 matrix. Okay, and let's look at the square of this. So this is, you can check that the square of that is going to be the following matrix, right? So one way to sort of think about this is that this diagonal, it's like a 1s gets shifted up by 1 every time you take a multiplication of it. And then that sort of happens more generally, okay? So if you take this 0, 0, 1, 0, 0, 0, 0, 0, 0, and you multiply it, well, actually, let me take this, okay? You can check that this just becomes the 0 matrix. Okay, so this is the H3 case, right? So H3 squared is this, and then H3 cubed is 0. So more generally, right, Hn to the n is equal to 0. So where the subscript n denotes the size of this matrix. Okay, so this is what is called a nilpotent matrix. So it's an example of a nilpotent matrix. So what it means, it's like for H to be nilpotent, it means that some finite power, it's like of that matrix vanishes. Okay, why is this significant? This is significant because if some finite power of the matrix vanishes, then if you were just computing the exponential of that, instead of having this infinite sum, you have a finite sum. Okay, so, but we're not quite there yet, right? Because we're not interested in just computing the matrix exponential of H, which is this nilpotent matrix. We're interested in computing the exponential of the Jordan block, which is lambda I plus H. Okay, so how do we go from there? Okay, so the way we go from there is the following. So e to the a is e to the lambda I plus h, right? Okay, but so recall, it's like I said, that in general the exponential of products is not the product's exponential, except when these two matrices commute with each other, which is to say that a times b is equal to b times a. Okay, and these two matrices do commute with each other because the first matrix is just a scalar multiple of the identity. So the identity times A is equal to A times the identity. So these two matrices commute. Okay, as a consequence of that, I can write this as e to the lambda identity, right, e to the h. Okay, so I can do this because the identity commutes with h, which is to say that IH is equal to HI equals just h, right? Okay, so you have that. So I know how to take the exponential, right? So e to the lambda times the identity, and then you have EH, okay? Then EH, it's like you have to compute. So that's going to be e to the lambda times the identity. EH is just going to be the identity plus h plus 1/2 h squared all the way up to 1 over n factorial h to the n. Okay, so, all right. And again, the reason why that happens is because, it's like this type of nilpotent matrix, it's like if it's an n by n matrix where the only non-zero entries are this diagonal ones, it's like just above the main diagonal, right? If that's an n by n matrix, then the nth power of it vanishes, actually. So I guess it's just, you only need to go up to n minus 1 then, right? Okay, so 1 over n minus 1 factorial hn to the n minus 1. Okay, yeah, so that's basically what ends up happening. Okay, so so the basic idea then, so we've looked at 3 important cases. The case where A, it's like the matrix is just a diagonal matrix. The second case is when the matrix has a complete set of eigenvectors. And the third case is that when A is a Jordan block. Okay, and so what we're going to see basically is that, we're essentially going to talk about what is called the Jordan canonical form. And so you're going to write some matrix, it's like in terms of the Jordan canonical form, right? And the Jordan canonical form will decompose, will give you a factorization of the matrix, which decomposes it into the central piece being a block diagonal matrix consisting of Jordan blocks. Okay, so what we'll see then is that we can put all these things which we've discussed so far together to then compute the matrix exponential in general. Okay, so let me just stop here for now.